previous class you studied what is conductor, what is semiconductor, insulator, what are the types of semiconductors, N-type, P-type, different types of materials in semiconductor, silicon, germanium. Again you studied that P-type semiconductor, N-type semiconductor, operation of PN junction diode in forward bias, reverse bias and no bias. The next topic is diode current equation. Diode current equation. In the previous class I told that in the forward bias condition for germanium or for silicon, the current increases after the threshold voltage exponentially. Why it is increasing exponentially, we will know by using this equation, diode current equation. The diode current equation is given by I is equal to I naught into e power v by eta Vt minus 1. This is nothing but the diode current equation. I equal to I naught into e power v by eta Vt minus 1. This is nothing but the diode current equation. I will call this as a number, I will give the notation star, where I is diode current and I naught is, this I naught is reverse saturation current. This is saturation current. That is nothing but the I naught. I naught is saturation current. E is nothing but the exponential term, and where V is applied voltage, which is positive for forward bias and it is negative for reverse bias condition or operation, where eta is a constant. Eta is a constant and 1 for germanium and 2 for silicon, where Vt is volt equivalent temperature. Approximately at room temperature, this value is equal to 26 millivolts. At room temperature, at T equal to 27 degrees centigrade, this value Vt, that is equal to 26 millivolts. So this is nothing but the what? The diode current equation parameters. I naught is the saturation current, or you can call that as a reverse saturation current. V is the applied voltage, positive for forward bias, negative for reverse bias, and eta is nothing but the constant. So 1 for germanium, 2 for silicon, and Vt is nothing but the volt equivalent temperature. And that value at room temperature, T equal to 27 degrees centigrade, the value is nothing but the 26 millivolts, constant value. Consider this diode current equation for forward bias condition and another one for reverse bias condition. First thing we will consider for forward bias condition. P type of the diode is connected to the positive terminal of the battery and N type of the diode is connected to the negative terminal of the battery, which is nothing but the forward bias condition. This during diode current equation for forward bias condition or operation. Okay, forward bias condition or operation. We know that the applied voltage is V and which is positive. Applied voltage is positive. I will consider 2 volts. And I am considering the silicon diode, therefore eta is equal to 2, constant value. We know that Vt at room temperature, Vt equal to 26 millivolts at 300 degree Kelvin or 27 degree centigrade. Therefore, by substituting all the values to this, I equal to I naught is a constant value and E power V is the applied voltage, I am considering that as a 2 volts, and dividing by eta is 2 is a constant value, again Vt is 26 millivolts minus 1. By simplifying this, we will get So 2 get cancelled, and this one 25 or 26 millivolts. So this is what I can write this as I equal to I naught into e power milli in the denominator. It will go to the what? Numerator. It becomes 1000. I equal to I naught into e power 2 get cancelled. It becomes what? 40 minus 1. Observe here, e power 40 is a large value compared to 1. We can approximate e power 40 is very much larger than 1. We can retain the first term compared to second term. Therefore, for the forward bias condition, the current is given by IF, and I can write this as I naught into e power V by eta Vt. So I am neglecting the second term, that is 1, because it is very small value. IF equal to I naught into e power, I can write this as Vf. Vf means forward bias voltage. This is nothing obtained in the forward bias condition. That's why the current in the forward bias condition is exponential increases. So you can see this is the voltage Vf and this is the current IF. In this, after threshold voltage for the silicon it is 0.7 volts. After that voltage, the current increases exponentially because by using the diode current equation. The diode current equation for forward bias condition. I am considering the diode current equation for reverse bias condition. In the reverse bias condition, the voltage V is negative. I am considering that as a minus 2 volts, and eta, it is a constant for silicon, it is 2. A volt equivalent temperature, that is volt equivalent temperature, which is 25 or 26 millivolts for the silicon diodes, it is constant. I can write by substituting these values to the standard diode current equation. I can write this as I equal to I naught into, and we know that I naught is constant, it is reverse saturation current. I naught into e power V means what? Minus 2 dividing by 2, again 25 or 26 milli minus 1. 2 get cancelled. Again it becomes I naught into e power minus milli, that is it becomes 1000 by 25. Therefore minus 1 or minus, this value is minus, so therefore this is 25 40, that is e power minus 40 minus 1, that is I naught into e power minus 40 minus 1. E power minus means the value is very small. E power, and that power is minus. Minus means we can write this as e power minus 40 as 1 by e power 40. E power 40 is very large value which is present in the denominator. So this becomes a small value compared to 1. E power minus 40 is very small value. E power minus 40 is very small value means by using this standard equation, the first term is very much lesser than the value 1. We can say like this, V by eta Vt is very much smaller than the value 1. We can write e power V by eta Vt, e power this is minus, so this is very smaller than 1. 1 is larger than the what? This e power V by eta Vt, because e power minus 40 is very small value. Therefore, approximate the diode current equation in the reverse bias condition, which is nothing but the IR, that is equal to I naught into, this function is neglected, and this equal to minus 1. I naught into minus 1. Therefore, IR, that is equal to minus I naught. We studied that in reverse bias condition, the current, that means in characteristics, this is what IR, this is what VR, the current increases initially, this is in microamperes and this one is volts. This is minus 2, minus 4, minus 6. This is 10, 20, 30, 40, like this. So the first, the current increases. After that, it becomes constant. Again, if you are increasing the voltage, reverse bias voltage, the current further increases suddenly, and this leads to damaging the diode. This voltage is nothing but the VBR, breakdown voltage. Okay. In the reverse bias condition, the current is constant throughout the voltage. After, if you are increasing further that ratings, then it will lead to damaging the circuit. Okay. The next topic is diode approximations. Diode approximations. In the last topics, you studied that the diode minimum voltage to turn on the device is nothing but the threshold voltage. What is threshold voltage? The threshold voltage, it is the minimum voltage. From that voltage, the diode starts conducting. That is nothing but the threshold voltage or cut-in voltage or minimum voltage. Therefore, in this diode approximations, we have three diode approximations. The name indicates that approximations. It is not the practical one, it is the approximations. The first one is ideal diode approximation. Ideal diode approximation. The second one, second approximation. Number 3 is piecewise linear model approximation. These are the three approximations. Ideal diode approximation, second approximation, piecewise linear model approximation. We will discuss ideal diode approximation. The name indicates that the diode is ideal. Means there is no threshold voltage. VTH is equal to 0 volts. There is no threshold voltage. The threshold voltage is 0. That means from 0 voltage only the current increases. That is nothing but the ideal diode approximation. For example, consider that the characteristics. This is VF, IF, in this VTH equal to 0. 0 volts. Now, this is the IF along y axis and VF along x axis. At the point of threshold voltage, we are considered in the previous explanation, that is forward bias condition. After threshold voltage, the current increases exponentially. But in this ideal diode approximation, there is no threshold voltage. The threshold voltage is 0 volts. So at 0 voltage only, the current attains to a maximum value. The current attains to a maximum value. This is assume that in milliampere, means assume that this is what 80 milliamperes. This is at 0 volts. At 0 volts only, the current is maximum. This is nothing but the ideal diode approximation. The second one is second approximation. In this second approximation, the diode has threshold voltage. For germanium, it is 0.3. For silicon, it is 0.7. At threshold voltage only, the current attains to a maximum value. That means it has threshold voltage. Threshold voltage for germanium, it is 0.3 for germanium. And threshold voltage for silicon is 0.7, which has threshold voltages. What are threshold voltage? Minimum voltages. 0.3, assume that this is the voltage, this is the current. 0.3 threshold voltage for germanium and 0.7 for silicon. Below that 0.3 volts in germanium, below this value, the current is 0. When it reaches 0.3 threshold voltage, the current increases suddenly. This is nothing but the second approximation for germanium. Similarly for silicon, below 0.7 the current is 0. After at 0.7 the current increases suddenly. Second approximation, the current attains to a maximum value at threshold voltages. At 0.3 for germanium maximum, at 0.7 for silicon it is a maximum value. This is second approximation, but it is also not in practical. When you apply the 0.3 or 0.7, the current won't be a maximum value, it will damage the circuits. Okay. The third one, piecewise linear model approximation. The name indicates that linear model approximation. In this, it has threshold voltage. After the threshold voltage, the current increases linearly with respect to voltage. Observe this characteristics. This is V and this is high voltage and currents. So 0.3 for germanium and 0.7 for the silicon. Below this, the current is 0. After threshold voltage, the current increases linearly with respect to voltages. Current increases linearly. So for silicon, for germanium, and this for silicon, below 0.7, the current 0. After 0.7, increases linearly. This is nothing but the piecewise linear model approximation, and this also not in practical cases. For the practical cases, we are concentrating on the exponential expression. Okay. Now we are considering applications of diodes. Application of diode. You studied that how many types of diodes: operation, forward bias operation, reverse bias operation, and diode current equation, and approximation, etc. The next is application of the diode. The main application of the diode, the first one is acts as a switch. Diode acts as a on and off switch. And the second one is, it is the main application is rectification. Rectifier. It is used as a rectifier. What is the meaning of rectifier? Rectifier is nothing but a device. So it is a device which performs the rectification operation. It is a device which performs the rectification operation. What is the meaning of rectification then? So the rectification is nothing but converting AC into DC, either voltage or current, where it converts AC to DC. This is nothing but the main application of the diode. Here in rectifiers, again there are different types. Types of rectifier. Off wave rectifier. The second one is full wave rectifier. There are three types of rectifiers: off wave rectifier, full wave rectifier, bridge type rectifier. Why it is called as off wave rectifier? In this, only half of the input cycle, input voltage, is converted into DC. Half cycle of AC is converted into DC, hence the name called as the off wave rectifier. What is full wave rectifier? In this, full cycle of the input AC is converted into DC, or called as pulsating DC. What is bridge rectifier? This is the advanced version of the full wave rectifier. In this, it converts full cycle of AC into full cycle of DC, and this is the one we are using for practical applications. Bridge rectifier is used as a practical application where you can use this in laptop chargers, okay, chargers, mobile chargers, etc. So this is the main applications we are using the bridge rectifier. Bridge rectifiers are used for the practical applications. We will discuss in next class in detail half wave rectifier, full wave rectifier and bridge rectifier. Thank you.